Hi everyone. Today I am going to talk about Hyperledger Fabric. There are many other great projects under the larger Hyperledger umbrella, such as Sawtooth, but as I am not an expert in those other projects, today we will be sticking with Fabric. Why Fabric? The market consensus is that Hyperledger Fabric is the market leader in enterprise blockchain. Looked at more broadly, through the recent Forbes Blockchain 50, Fabric is the #1 platform, followed closely by Ethereum and Corda, a distant third place. The diverse set of companies using Fabric proves its bona fides in the enterprise. There are, however, a number of technology-related myths and hidden sharp edges that architects and business leaders looking to adopt Fabric should be aware of. The motivation for this presentation was to help others avoid or prepare for and overcome the challenges I experienced in the last 4 years using Fabric to create solutions and develop the ledger itself. Through frequent presentations on Fabric internals, I have had good discussions about the unique design and operations aspects that universally surprise those familiar with other blockchain systems. Through this presentation, I hope to 1. Reveal areas where those unfamiliar with Fabric's inner workings will run into trouble. Slice through marketing hype with X-ray vision to help you make clear-eyed decisions. And for each potential limitation in the as-is product, show how it can be designed or coded around thanks to Fabric's flexible modular design. At the end of the day, in spite of a few rough edges, I strongly feel Fabric is the best of the first wave of enterprise blockchain systems. So, a little bit about myself. I worked at IBM and IBM Research in the United States and China for the last 12 years, developing database engines. Informix, DB2, Fabric, Datamirror, BlueSpark, SolidDB. I was the chief architect of a Shanghai blockchain startup for a couple of years, focused on Hyperledger Fabric for industrial IoT and supply chain management. And during that process, I gained significant experience creating extensions for Fabric, including support for MongoDB, multiple collections, indexes, backup and restore, offline and online data verification, and writing cloud HSMs. I had multiple customer engagements using Hyperledger, including the Interbank payment system for the Monetary Authority of Singapore. The material in this presentation primarily came from two sources: problems I experienced in the last 5 years using Fabric, and through recalling discussions I had with others when teaching about Fabric. The topics in this presentation are divided into 3 categories. 1. Programming model. 2. Security. And 3. DevOps. Our first myth. Most modern applications use a 3-tier architecture with an application server acting as the middle tier, supplying an HTTP API and business logic called by the web client. Current best practice, application servers often implement this MVC architecture using Node.js or Java. When Fabric added support for these languages, it was all too easy to conclude that an MVC architecture could be employed when crafting a solution. While a Fabric application can be developed in this way for demonstration purposes, in practice, the security implications of this will likely prove unacceptable to any party interested in the security afforded by blockchain. Non-repudiation is the first tenet any secure system should afford. This means we should be able to positively assert that if a transaction is signed using Alice's private key, then no party other than Alice could have signed for her, and therefore she cannot deny her involvement and responsibility. By introducing an application server responsible for signing transactions on the blockchain, we have delegated this responsibility to a third party and can no longer confidently assert Alice's involvement. The application server, as the business logic implementer, also serves as a custodian of Alice's private key to sign a transaction on her behalf. In Fabric, applications primarily address business-to-business needs. As such, each organization may have an internal application server that authenticates local users and signs blockchain transactions on behalf of the organization using the organization's identity and private key, rather than that of an individual. Ultimately, as each organization is responsible for the actions of its members, this should be equivalent from a partner's perspective. Internally, the organization should keep careful audit records of internal users performing actions on the blockchain to determine responsibility. Alternatively, a more traditional two-tier architecture can be used by developing a native application to be run on a desktop or mobile device. This native application can interact with a local secure enclave or HSM to sign transactions. If a lightweight, web-friendly application delivery mechanism must be provided, an alternative such as use of a cloud HSM or virtual HSM with multi-party computation for signing can be utilized. So, on the left here, we have a traditional three-tier architecture: web browser, application server, and Fabric. This browser provides the user interface, the app server contains the business logic, and Fabric provides the smart contracts and database. Often this business logic implements privacy or access control rules that cannot be trusted to run in a browser client. If we move to a two-tier architecture, this logic would need to be contained fully in the smart contract code. Our next myth: with support for Java and Node, any programmer can write smart contracts. Fabric support for developing smart contracts in Node.js was added in version 1.1, released in early 2018, and for Java in version 1.3, released in late 2018. But most importantly, Fabric 1.4, released in early 2019, introduced an improved programming model for Node.js and later Java with 1.4.2. These improvements have obviated the need for Composer by baking modeling abstractions into the smart contract language and have been a significant boost to developer productivity, code readability, quality, and maintainability. However, there are many areas where developers will need to understand the Fabric transaction model to optimize performance. Just as with many other blockchain systems using key-oriented ledgers, having a fat value that may be modified for more than one reason can significantly impair performance. Much like Robert Martin's single responsibility principle, each row should be narrowly aligned with its purpose. A row serving multiple functional areas will become a hot row with a high potential for write conflict. With Fabric, if multiple transactions are updating a particular key within a batch, which is a block antecedent, all transactions subsequent to the first will be rejected, as the read set key version no longer matches. So, the solution is to decompose the asset value into finer-grained pieces stored at different keys. In this way, multiple pieces can be manipulated independently as part of a single batch. As a simple example, consider a company that manages a fleet of vehicles. The original data model might have a single company asset with a nested JSON array of documents storing each vehicle's maintenance and usage information. If done this way, only one vehicle can be updated per block. However, if each vehicle is stored as a separate row, and therefore key, they can be independently updated in a single batch. A suitable key could be generated by combining the company ID with the vehicle ID in a way that creates a unique value. Our next myth is a direct quote from the Fabric 1.4 channel documentation, and it says, "No ledger data can pass from one channel to another." This is simply untrue. The reality is that while cross-channel transactions cannot write data to another channel, data can be read. Put simply, even if a cross-channel write is performed as part of simulation, it will not appear in the read-write set, and therefore will not appear in the ledger as part of the commit process. As proof that cross-channel reads can be done, let us briefly look at the development of the interbank payment system for the Monetary Authority of Singapore as part of Project Ubin. The cross-channel funds transfer process relied heavily on this existing capability. In this figure, we have three channels: one for banks 1 and 2 talking, one for banks 1 and 3 talking, and one for anonymous fund transfers. The reason we divide up banks into bilateral channels is to avoid revealing total liquidity to other banks. This introduces the problem of not having enough liquidity in a bilateral channel to serve as a fund transfer request. To resolve this, we need to rebalance the liquidity of a bank by moving funds between bilateral channels. To avoid funds creation, we define the concept of anonymous fund transfers. In the fund transfer process, example shown in the figure above, Bank 1 is moving funds from its channel to talk with Bank 2 to instead talk with Bank 3. At each step, either Bank 2 or Bank 3 acts as a guard to ensure no funds are created or destroyed by Bank 1. When the anonymous fund is created in the multilateral transfer channel, Bank 2 performs a cross-channel read against the Bank 1, Bank 2 channel to verify its creation. Similarly, when the funds are imported into the Bank 1, Bank 3 channel, Bank 3 performs a cross-channel read to the multilateral transfer channel to verify the fund amount. To guard against misuse, there are additional mutex-like features that lock the funds in the Bank 1, Bank 2 channel while the creation of the anonymous fund is taking place. When initiating the transfer process, a pause is placed on the funds of Bank 1. Then Bank 1 creates the anonymous fund in the transfer channel. By pausing the bilateral channel activity, Bank 2 can easily verify through a cross-channel read that Bank 1 created the anonymous fund with the correct amount. After this step, the bilateral channel activity can be resumed. If after creating the move out anonymous fund, Bank 1 wishes to reverse the process, they can call the cancel move out anonymous fund method to credit back the money to their account. This might be done if sufficient funds become available in the Bank 1-3 channel to satisfy the transfer request. Having created the anonymous fund, Bank 1 now wants to move it in elsewhere. First, they must lock the anonymous fund to the channel it was designated to move into. This prevents double spend by moving it into multiple channels. In the Bank 1, Bank 3 channel, the move in anonymous fund method is called to credit Bank 1's account, with Bank 3 verifying, via cross-channel read, that this was the channel designated for the receipt of funds. Finally, to mark it as spent, the anonymous fund is cleared. Our next myth. Fabric supports heterogeneous databases. It is true that Fabric supports a pluggable database model, with built-in support for LevelDB and CouchDB. And via plugins, you can author any new database support you wish to add. However, if any smart contract uses the rich query feature of CouchDB as part of a smart contract, then all peer organizations will likely also need to adopt CouchDB to successfully perform transaction simulation. In theory, a commit-only peer could still work, as it does not need to run the smart contract. Looking further into the future, as multiple networks merge, just as companies merge and subsequently seek to integrate and normalize IT systems, there will be a similar need for Fabric to support a migration path. Perhaps someday smart contracts will be written in a way to support multiple databases, with chain code specific to the local flavor. This could come in the form of a layer similar to Hibernate for relational databases that performs object relational mapping and SQL query generation. One vision of a system that implements this idea is the Digital Asset Market Language, DAML. DAML is a functional language, inspired by Haskell, where users describe assets and business processes. DAML is relatively new, and time will tell if it is the correct answer. In my opinion, either it or something very similar will likely be the endgame for smart contract development, as it avoids storage and execution dependencies. Until the market coalesces around a specific technology solution to abstract these issues, the best bet is to go with CouchDB or another document-oriented database. This form of database can be mapped easily to other database models and provides greater flexibility to define indexes and perform analytics and other queries via the database rather than requiring complicated logic be written in the chain code. This abstracts away complex details and improves reliability. On to our next topic, security. Our next hype-related subject deals with the channel policy mechanism. The built-in chain code channel endorsement verification policy mechanism, introduced in Fabric 1.1, claims to enable transaction-related party endorsement. Recall briefly that the endorsement policy is a textual specification using Boolean operators and an OR and grouping via parentheses to specify the endorsing organizations and roles within those organizations that must be present in a transaction to be considered properly endorsed. For example, this might be ands between organization 1 member, organization 2 member, ors between them, or more complicated and or combinations between members of different organizations. Unfortunately, the built-in VSCC, Verification System Chain Code, policy mechanism has two significant shortcomings. One, it cannot be specified on a per method basis, and two, it cannot refer to arguments within the method. If the policy could be selected on the basis of the method being invoked, we could have a single chain code deployed where simple methods such as transferring between two participants required only two endorsers, and a configuration-related method required the majority or all to endorse. If the policy could refer to method arguments, such as the organizations involved in the transaction, it could be more narrowly tailored to close a critical security hole. To demonstrate this more clearly, let us consider a scenario wherein a channel contains three participants, Alice, Bob, and Charles, and a single smart contract has been deployed to manage the ownership of assets. The channel participants primarily make use of a transfer method that takes two arguments, the asset ID and the new owner. To be properly endorsed, a transfer should be signed by a member of each organization participating in the transaction. For example, if Alice is transferring an asset to Bob, it should be endorsed by A and B, Alice and Bob. Looking at all possible pairs, we can calculate the endorsement policy in the channel should be A and B, or B and C, or A and C. Written in Fabric's Polish notation, we have OR of and AB, and BC, and AC. While this policy clearly covers the transfer from Alice to Bob, it also must cover Bob to Charles and Alice to Charles, as they could also transfer assets. This means that potentially the transfer of an asset owned by Alice's could be endorsed by Bob and Charles, forsaking Alice. Thankfully, this clearly unacceptable situation has a solution. We can use Golang to create a custom verification system chain code policy that inspects the method and arguments to enforce meaningful business-level endorsement verification. Our next myth. Fabric channels solve all of your data privacy problems. Fabric's channels, introduced with 1.0, were a first attempt at local data partitioning and physical isolation by providing a faculty that can ensure a set of data only traverses the networks of and is only stored on the disks of a subset of the organizations that are members of the blockchain network. The rationale was simple. Banks and others with high security transactions were uncomfortable with data even when encrypted being physically present on peers controlled by other organizations unless necessary. The reality is that the ordering service is a single point of trust. All transactions on a channel flow through it. As a central banker, this is a good thing, as it represents a single point of control and auditability. But as an organization interested in a decentralized solution, this is a bad thing. The solution you want to go with depends on your objectives. A consortium might prefer to use a centralized ordering service to regulate its members. However, most organizations will prefer to use private collections. Looking at this, as shown in this diagram up above, after gathering the required transaction proposal endorsements, a client application submits the simulated and endorsed transaction for ordering, such as to a Kafka cluster. After ordering, the transactions within a time window are grouped into a batch. The ordering service then broadcasts this batch to all organizations' committing peers to be verified and transformed into a block of valid transactions. While the local data partitioning goal was achieved, the ordering service represents a single point of trust as all transactions for channels it manages flow through it. The issue isn't what is possible theoretically, it is what is practical when scaling a solution. For a small test network, having a distinct ordering service for each channel is plausible and would provide the requisite data partitioning and isolation at both the peer and network level. At a practical level, for many scenarios, the overhead and multiplicity of ordering services that would be required is often impractical. The next myth fills us in on the details. On to the DevOps section. Myth: channels are free. The reality is, channels multiply like crazy in many real-world scenarios. In fact, they multiply quadratically, to be specific. When creating the Interbank payment system for Singapore Central Bank, the Monetary Authority of Singapore, our network needed to support a little over 200 banks privately communicating with each other through bilateral transfer channels to ensure no information would appear in other organizations' ledgers. This meant that each bank had approximately 200 channels to talk with other banks, and each of those banks similarly had approximately 200 connections. In graph theory, this is called a complete graph. In networking, it's a fully connected mesh topology. The number of connections is proportional to n squared, and thus, even in Little Singapore, this results in over 20,000 channels. In the United States, with nearly 7,000 banks, you would need over 20 million channels. The ordering surface simply wasn't designed to handle so many channels and would become quite slow. For example, in a test network with 10 banks, you would have 45 bilateral channels. Just creating these 45 channels takes approximately 90 seconds at 2 seconds per channel. For 20,000 channels, a rough time estimate was 11 hours. For the USA with 20 million channels, it would take approximately 1.5 years simply to create the channels. If you want to ensure complete channel isolation, you would also need to approximately operate 20,000 Kafka clusters. This just isn't practical, and a better solution is required: private collections. So given the shortcomings of channels, it should come as no surprise that the Fabric team started searching for a better solution shortly after the release of 1.0. The idea we settled on was originally called side channels, but became productized as private collections. This enables organizations to establish private databases that a subset of organizations are allowed to see. The transaction data from these is never sent through an external ordering service. So although the ordering service is no longer a trust or performance problem, instead a peer-to-peer network must be established between organizations' peers. These P2P private collections are defined in a JSON file, specifying the organizations that can see the contents. In the Singapore example, this file would need to specify approximately 20,000 pairwise combination of banks. This change places much more burden on the network administrators to appropriately define the routes and private networks, perhaps VPNs, to create a secure foundation for communication between organizations. Although burdensome, this all sounds good. Here's an example of one of these private collection policy files. It's a JSON document, and as new banks are added or removed, or the banks merge, this document would need to be updated to match with the new configuration. And as you can see here, you give a name of the collection, you give a policy that's an and or type of organizations and members, number of peers, how long does it live, etc. Our next myth: data privacy is easy. Continuing with the theme of data privacy, even with channels or private collections, the act of slicing up your overall asset pool into hundreds of bilateral partitions introduces its own challenges. Returning to the IBPS example, if you divide your bank's overall liquidity 100-fold to avoid other network participants having a total view of your liquidity, it is now more difficult for you to access it all at any one time. Simple acts like computing your total liquidity requires cross-channel or collection queries. When performing a transfer, it is now much more likely that insufficient liquidity will be available in a given channel or collection. To resolve this, money must be transferred from another private collection in a way that ensures no funds are created or destroyed in the process while preserving privacy. And, unfortunately, there are other caveats. To deal with ordering and read-write set MVCC consistency, the public transaction used to record the private transaction occurring must include the read set keys. Therefore, if you are in a situation where even revealing that there has been activity on a particular key is unacceptable, you will also need to salt and hash the keys to avoid revealing this to others. The salt used for a particular key will either need to be stored off-chain or as a value in another row that enables lookups. Only by blinding the key can we prevent other organizations from becoming aware of activity. To deal with all of this requires that you hire smart programmers familiar with cryptography and distributed systems, such as multi-party algorithms and homomorphic encryption, to develop custom solutions. Fabric, in contrast with many other blockchain systems, has many components that an administrator must become familiar with to operate. Peer, CouchDB, ordering services using Kafka, Zookeeper, Raft, membership services providers, Docker. It also requires specialized routing and firewall rules to establish secure communication links between organization peers, MSPs, and the ordering service. Additional administrators will need to be involved with the management of a multi-organization certificate authority. To resolve this, IT network engineers need to work as part of a consortium to determine the appropriate way to expose their peer to other organizations, to receive transaction endorsement proposal and simulation requests, while keeping an attacker's ability to gain access to sensitive information stored in the simulating peer's database limited. One way to simplify this effort is to co-locate all organizations' peers within a single data center or provider. Of course, being in a single availability zone is a risk unto itself. When dealing with mission-critical systems accessing core records, you need a team of highly skilled network engineers and system administrators on board to plan appropriately. These diagrams show potential topologies for deployment, and I'm going to go through a series of different peer, network, and component diagrams that show some of the complexities that come into play when deploying Hyperledger. So in the top left is a simple single-tenant owner-operator network. In this, organization 1 controls all the peers in the ordering service, and there are a number of satellite organizations that access the hub. A scenario where this might happen would be with a large company, such as Walmart, that wants to have total control over all of these peers and uses its market power to compel suppliers to participate in their network. On the lower left is the first introduction of a multi-party system where two organizations are operating the peers, acting as a hub for their respective suppliers. Finally, on the right is a situation where each organization operates their own peer. There may still be a controlling organization, such as a consortium operating the ordering service or other top-level services, such as membership services. This diagram gives an example of the components and network partitioning you might see in a typical deployment. Within an organization, there's the DMZ for traffic requesting, transaction proposal simulation, and endorsement from other organizations, as well as validating and committing batches that are distributed via the ordering service. There's an internal server subnet where existing application servers such as a WMS, ERP, etc. are operated, and tools such as an Oracle broker and replication services are used to query and synchronize information from these existing systems into the blockchain. There will also be a peer network where services such as Fabric, its ledger, and specialized chain code containers operate. The ordering service is placed in the cloud to maximize availability and performance to all organizations. This diagram shows a typical set of Fabric components for operating blockchain at an enterprise scale. Some components, such as membership services and infrastructure services, may already be operating within your enterprise. But this just shows that there are a lot of moving parts that are involved in an enterprise scale deployment of Fabric that you need to have a team that's able to deal with and understands how to use them, secure them, and scale them. Fires, earthquakes, tornadoes, lightning, floods, hurricanes, disasters happen. If all Fabric peers are in the same data center, locale, and suffer a direct hit, only a remote backup will be sufficient for recovery. Crypto ransomware is ever present, and a blockchain system is a prime target. If all online volumes are encrypted, having an offline backup prior to the attack provides the option to reject paying the attacker's ransom demands without complete data loss. Even in less disastrous scenarios, recovery by replaying the block log from the Genesis block can be painfully slow. Private collections complicate this further as it is insufficient to perform a backup at a single peer. Each organization may have a unique set of private data not fully visible at any other peer. For example, if private collections exist AB, BC, AC, then each organization should be performing independent backups, although not necessarily at the same time. Sadly, the Fabric team does not agree that backups are a necessity, but there are two strategies you can use for backup: offline and online. If you take a peer offline temporarily, this is the easiest option. If you are using private collections, remember that all organizations with unique access to a private collection will need to perform a backup. So by simply taking the peer offline, you can make a copy of all of the data, bring the peer back online, and continue processing transactions. To perform an online backup, we must have a consistent version of all blocks, indexes, and logs. A no-code solution would be to use LVM and volume snapshots. A better solution would be to pause Fabric processing commits and use a native backup tool for the database to ensure a consistent restore point. All blockchain systems are, in essence, unbounded, append-only logical logs. Storing all data from the Genesis block onward and maintaining it has a non-trivial cost. One way to mitigate this cost in a production deployment is to use hierarchical storage to reduce the cost of storing old blocks. To increase the value of storing those old blocks, the History API should be enabled so that users can access records that aid in fraud detection, KYC, AML, and similar efforts. The ordering service is a significant source of network congestion. All transactions must flow into at one time and are replicated out to N organizations. This problem grows quadratically with the number of organizations. If N is the number of organizations and T the number of transactions per second per organization, the total transactions per second being handled by the ordering service is given by the formula N times T times the quantity N plus 1. This problem is somewhat mitigated by organizations using gossip to replicate internally between peers within that organization. The long-term solution to this problem is to have a gossip-based transaction distribution mechanism to eliminate the need for the ordering service to directly talk with all organizations. So let's look at an example of the bandwidth required. The minimum transaction proposal size is approximately 0.6 kibibytes. A proposal endorsement is 1.4 kibibytes. In the end, that means we need 3.4 kibibytes to and from the ordering service for each committing peer. So if we look at simple scenarios here where we have a transaction, for example, we are on let's say we had a 1 gigabit Ethernet connection to the internet. If we had 2 endorsers and 2 committers, then we would require approximately 14 kibits per second to do those transactions. And on our 1 gigabit network, we could do approximately 8,800 transactions per second. Looking at a much larger organizational network, let's say we still just had 2 endorsers, but we had 128 committing organizations. That would require 442 kibits per second, meaning that we could have a peak throughput of only 282 transactions per second. Some final thoughts. Many of the issues discussed herein have analogs in other blockchain systems. As enterprises look to blockchain, they need to think deeply about organizational issues as well as technical. Adopting blockchain is not simply about running a parallel database mirroring existing OLTP systems. It is about developing new models for business made possible through enhanced trust and information sharing. Technologically, blockchain makes this possible through a common view of information, non-repudiation of transactions, and access to immutable historical information. Leaders need to consider issues such as, will users transact as themselves, or will transactions be signed by the organization they are acting on behalf of? Will you organically grow, hire, or contract expertise in Fabric to deploy smart contracts that are both performant and secure? How are you going to design effective smart contracts that create true counterparties that have a vested interest in holding others accountable? Looking to the future of the business, how should systems be architected to deal with the possibility of systems integration due to mergers and divestments? When acting as part of a consortium, what is the governance model that will be used for smart contract development? How will core systems be exposed to other organizations as required for peer endorsement? In answering these questions, leaders should recognize that experience matters, both with blockchain and within the domain they operate. The journey to blockchain adoption is a marathon, and they should start to build in-house experience today, especially for DevOps and networking. Adopting Fabric or any blockchain system as an integral part of a business requires thoughtful analysis to maximize the ROI. Existing efforts at digitalization and a concrete understanding of existing business processes are critical to success. When Fabric 1.0 was being designed, it was not clear what the emerging business model requirements would be. The hope was to be sufficiently flexible to provide a good starting platform given broad configurability and modularity. As the most enterprise-ready of the first wave of blockchain products, there are few situations for which Fabric cannot be adopted. However, successful adoption requires significant expertise in networking, security, routing, cryptography, game theory, databases, containerization, and distributed computing. Just as Rome was not built in a day, nor will the future of business and blockchain. How to eat an elephant? Grab an ear and get chewing. Thank you very much.